Hi everybody, and welcome to session 5 of our Talking Shop with Tony series. And this week I'm talking about cheating and nonlinear buckling, a slightly tongue-in-cheek type of title. Now the webinar teaser, the promo that I put out, it actually was based on a real-world experience. The first time I ever tried to do nonlinear buckling analysis, I actually got into trouble because I just applied the load to a cylinder, and the cylinder just basically started long and it just foreshortened. It got short without any kind of indication of buckling. Now luckily the cube I was sitting in, just down the way, the head of development, nonlinear development, was sitting there, and I kind of said to him, well, what do I do? He came over and said, Tony, we've got to cheat. So that was basically the idea behind this presentation. So the idea is we have to do a little bit of cheating, and what is the nature of that cheating? Well, what I did was I applied load and boundary conditions to a cylinder and expected it to buckle, and it just did this. And basically, because of the constraints, a little bit of stress concentration around here, there's no indication of buckling. In fact, it went straight through yield and just kept on going. It was obviously a ludicrous answer. I was expecting it to do a nice nonlinear buckling analysis, perform something like this. So nonlinear buckling analysis was going very wrong. So let's kind of backtrack. Let's set up an even and simpler case, and it's going to be a nonlinear case where we've just got buckling of a very simple rod, long rod. It's 180 inches long. It's just a rectangular cross section, and the boundary conditions are that it's a guided type of rod. So it's fixed at one end and it's guided at the other end. Now if you ever try this little experiment with a drinking straw, say in Starbucks or somewhere like that, if you're allowed to buy drinking straws these days, if you get a hold of the end of the rod and try and squeeze them together and try and keep them parallel, actually requires quite a lot of force to actually do that. So this is what we're setting up in here. Now the length, as I said, is 180 inches. The radius of gyration, which is a measure of the dispersion of the material, is 0.730. So armed with those two figures, we can actually do some back calculations. We can use an Euler type method to say, is this a slender rod, and should it buckle in a very simple kind of way? And we'll find that's actually the case. So I set up the nonlinear analysis and replicate exactly what I did way back in the day. I just apply an end load, and it's a nonlinear analysis, and this is showing the axial tip deflection against the load increment. We get up to 100% loading, and it just foreshortens, and it just basically goes straight through yield. And here's the stress contour plot, about 18,181 pounds per square inch psi. Yield is at 16,000 psi. So again, it's another kind of silly answer. So let's just back up a little bit. Nonlinear buckling didn't seem to work just with that applied end load. So let's see what linear buckling will do. Now that should work. Keep our fingers crossed here. And we'll talk about why it should work a little bit later on, as opposed to nonlinear buckling may or may not work. So this is just a rectangular section. Here's the dimensions. Key thing for me is the cross-sectional area, and this is the radius of gyration calculated by this particular app in here. Now armed with that, I've got an elastic modulus. It's aluminium, very close to 1e⁷ pounds per square inch. And this is the Euler calculation. So it's split into two here. It's calculating the stress and then calculating the critical load. Normally it's the critical load that we're interested in. You can see the ingredients of the equation. It's the classic Euler type of strut equation. We've got the material constant, a Young's modulus. We've got K, which is a factor on the end condition. We'll talk about that in a second. L is the length and R is the radius of gyration. And then we've got the cross-section area. And that's essentially all we need to do this. So about 8,800 pounds force is what we should be using here. Again, I use Mechanicalc. That's an app online. This is free publicity for those guys. But hey, I paid for my license. They're not. I don't have any shares in the company. Perhaps I wish I did. So now I'm going to do a linear buckling analysis. So it's a special type of buckling analysis. It's not nonlinear. It's linear, and we're going to see the steps that we need to do carry out to do that. So the eigenvalue is 0.35. That eigenvalue is a factor on whatever arbitrary load that I applied. So I applied 25,000 pound force, I get 8755 comes out. So it's fairly close to the Euler calculation, but it's not quite there. So I get 8755 plays 8827. Now that's an irritating little error. It's a small percentage, but we'll look at that a little bit later on to see actually why we get that error. So the linear buckling analysis, just as a sanity check, that should work. But now the big question comes down to, okay, we did the sanity check, we did linear buckling, rather than my target is to do nonlinear buckling, but was the linear buckling analysis valid? There's a few things we need to think about here, and one of them is that particularly that length to slenderness ratio, and there's an L over R ratio here, which kind of gives us an upper bound on where the cutoff is going to be before we go from what's called slender theory, Euler type theory, a slender type structure or slender beam, to if we went all the way up here, this is basically showing us just the length of the beam. Our beam is 180 and it's sitting here and it's on this Euler curve, so it's the red curve here. I've got it transitioning up here to the Euler curve. Now if we think about it, if we apply enough load to a very short stocky strut, then that's just going to fail at the yield level, which is, as we said, is about 16,000. So somewhere between the nice long slender Euler strut, which we've got down in here, we're actually in that category. We've got a transitional category, so we call this like an intermediate kind of strut, and then something which is just not going to see buckling. Now there is a curve for known sections, such as rods, a lot of civil engineering sections, a lot of engineering classical beams that we can have, I-beams, box beams and so on. There's actually an interaction equation called the Johnson equation. For general type of structures, we don't know that, we just got to explore it. So the question here is, are we slender enough basically to get away with the Euler assumptions, the linear buckling type assumptions? And in our particular case, this particular applet again converts, because it knows the radius of gyration, it can just tell me directly what the critical length would be. So basically it's saying this is the transition. If I get a length about here, then I should be not using slender beam theory, shouldn't be using the Euler, shouldn't be using the linear buckling. So I'm okay at the moment, so that looks okay. So we saw there that my analysis, Euler analysis, FEA and the simple Euler analysis was giving me about the same kind of level. So everything looks okay because we've checked it against this idea of a slender beam. Again, in real life, it's a bit more difficult to actually check that, but this is a useful kind of way of doing it. Now I want to get my slender beam to work, but I wanted to get it to work in a nonlinear buckling way, not a linear buckling way, but nonlinear. So this is James Garner, one of my favorite actors. He's played a cowboy here. I don't know if he was the gambler or the guy that caught the gambler out. So it's basically of the card table saying, you pull that side load, which I'm going to apply here, and that's my cheat. So my ace up my sleeve here is to slip in a side load, 50-pound force. Why did you do that? So James Garner wants to know, and everybody else wants to know, why did I cheat? What's my justification for cheating? Well, so if I look at that side load, it's very small compared to the axial load. It's about 0.2%. I pushed it at the midpoint, so I'm giving this this rod, or this beam, a little bit of a side push. Now I finesse the cheat a little bit. So what I do is, this is the red curve going all the way up to, this is the ramp up, which is applied to the first load, which is 25,000 pound. So that just keeps going onwards and upwards till it gets to the 100%. My little push load, I take up to half the level here, so I actually take it up to, in fact, 25-pound force, and then I ramp it off down in here. So the load factor doesn't actually get up to the unit value of 50. I just take it up to 25, edge it back down again. That's finessing it. It's basically saying, if you catch me out with cheating, you don't catch me at the end of the cheat with a load in there. I've just subtly taken the load off. So it's like a push load, get things started, and then I take that load off. So if I do that, now my nonlinear buckling actually looks pretty good. This is over on the right hand side here is the initial condition, and then this is the buckling that's carrying on. You can see it gets to a pretty wild shape over here. Now I can actually chase that buckled shape through, and so it's developing a particular, and now it is a true shape. These are actual deformations. It's not an eigen mode or an eigenvector, which we have from the linear buckling analysis. And I've actually clipped the stresses here, plus or minus 15,000. So 16,000 yield. So we're getting yielding coming in here. So that, again, it is buckling. And this would perhaps be up to our valid load level here. Beyond that point, it's going plastic at some point. So really, to chase things through, we need to bring more non-linearity into the case. The first four here, what we call purely geometric nonlinear. That's basically got the buckling going. It's updating the stiffness matrix in the presence of the configuration change and putting some stress stiffening terms and so on in there. Beyond that, again, it should be yielding. So it's a kind of it's an interesting picture, but it's really a silly answer beyond wherever we got the kind of like the purple, or just over the purple, just over 16,000 psi in there. If we actually look at the load deflection curve, this is the load factor being applied. Remember, 25,000 was my top level, 100%. So as I come up here, I'm getting down to about somewhere between about 32% and 35% of that load, and these are the actual numbers of the force which is coming through. So this little series of pictures actually is going up to the point up to there. The linear value was either 8755 or 8827, somewhere in there. So it looks quite plausible in the sense that my nonlinear buckling now is pretty well agreeing with my linear buckling assumption. So that's good news. Two different methods, two actually quite different methods, are kind of agreeing because this is a slender strut. But one of the questions now comes to mind is, well, where does that buckling actually occur? And that's one of the problems we have, is that in a nonlinear buckling event, it isn't what we call a bifurcation, a rapid transition from one moment you have axial load and then you develop the lateral load, a lateral response. So this is the lateral response in terms of deflection shooting up in here. It's a little bit of a curve in here. So where do we nail that down? Where do we say that actually is? And that's a little bit difficult to actually decide where we're going to do that. 0.35 is here, and that gives me a fairly close number. 0.325, we could perhaps take a little bit more cautiously here, is a lower number. So in the real world, which is what we're trying to model here with the non-linear approach, it's a little bit more difficult to say sometimes exactly where that transition is going to occur. Now, this beam is rather curious. It does actually stiffen up again at a very large deformation. So as we go through here, this is our initial buckling. These are the initial plots we had here. Bear in mind, we're not putting in plasticity, so it's all a little bit artificial, but it's just interesting to kind of look to see what happens. We get to a very highly buckled state here, and at this point it's almost forming like a U-bend in here, and it gets to that point, and from here to here it exhibits another very interesting thing, which is called a snap through. It goes from one stable configuration here to another stable configuration here. So what this beam is doing is actually softening and then starting to stiffen up and then actually snapping through. And it's an interesting exercise in showing potentially what the nonlinear analysis can show us. It can show us the post-buckling type of behavior, what happens after we actually get that buckling point. Linear buckling analysis can't give us that. Now again, it's a little bit of a fantasy land because I didn't put plasticity in there, but we'll look at that a little bit later on. Initial buckling, when a nonlinear buckling, may have plasticity present prior to buckling, developed during buckling, but probably most structures pretty soon after they start to buckle, they're going to have a plastic mode. Now whether we're interested in that or not is another matter. Probably by the time we get to this point in here, we're pretty happy that it started to buckle, and that's enough for us. This is really just a collapsing type of structure. There's no real stiffness that we're interested in here. It's rather like a Coke can. If we squash the Coke can, it's starting to resist, it's stiffening up a little bit, then it's rapidly softening. It produces a series of plastic lobes as it starts to flatten out. So a lot of plasticity going on. It may stiffen up a little bit, but we're not really interested in that once it actually starts to collapse. So it's the same kind of idea here. We may or may not get interested in the post-buckling behavior, usually dependent on whether it's actually going to start to stiffen up again once it sees its initial buckle. So if we compare the linear buckling analysis with the non-linear buckling analysis, what we've looked at so far, this is a kind of zoomed in picture in red of the nonlinear buckling. We can see where exactly do we define that buckling occurring. With the linear, it's got what we call a bifurcation point, meaning applied load axially suddenly transitioning to a lateral response, and that kind of 90-degree change in response is what we call the bifurcation point. So we can only have that load increasing, and the linear buckling analysis gives us a value right at that point. What happens next in terms of the mode shape? I can see the initial mode shape. Is it accurate? Well, we'll talk about that a little bit later on. It gives us a particular kind of mode. What happens next? We just don't know. I sometimes liken this to when I used to go to Saturday morning picture show when I was a very young kid. They used to show the reels of the old kind of westerns, the sci-fi and all that kind of thing. You won't believe it, but I actually used to watch Buck Rogers in the original black and white. So the end of each reel on the Saturday, the hero's in desperate trouble, and you think, well, we know he's going to get out of it. So next Saturday we come along and see how he got out of trouble. Well, the non-linear buckling is like that. We see the next reel. We see what happens next. The linear buckling is like, there's no next Saturday. What happens? We don't know. We don't know if the hero survived or not. So linear buckling gives us an idea what may happen, but not what happens next. So there's some pros and cons in here. There's no knowledge of what happens after critical buckling. We do get a hard number, though, in the sense that we get a number. And that can often be quite useful. People like that because we want to put a margin against that. Now, again, is it a good number or not is another question, but at least we do get the number out. And there's also no cheat needed. And we'll see why there's no cheat coming up in a few slides. Nonlinear is a transition. It's not a bifurcation, well, not at least a rapid bifurcation. It's a slow transition from one to another. And generally, the way I describe nonlinear buckling, do we need nonlinear buckling? If there's evidence of a structure starting to have some behavioral response pre-buckling point, it starts to what I call moan and groan a little bit, and then it buckles, then it's almost certainly the kind of structure we need to do a nonlinear analysis in. This one, it's kind of on the fence. We could or we could not. We get very similar results. But we can explore the post-buckling. But the trouble is, what load level, what did it buckle? That's a bit of a debatable question we'll get into. And it only took just a little push, honest. That's all we needed to do to get it to go. So thinking about that push, I call this other cheats. What happens if we push 50 pound a little bit higher up, not in the middle? Well, in fact, in this case, there's no difference. And that's a good test of how valid our cheat is. We start off with some, and obviously the idea is we're putting some sort of imperfection in there. We're putting some eccentricity in there. The eccentricity picks up a moment. The moment starts to generate a bigger eccentricity, and away we go. Both of these transition into a shape, and I won't call it a mode shape. It's a buckle shape, which is and they're almost identical. And so in this particular case, they happen also to be the same mode shape as the first eigenvector from our linear buckling analysis, but that's not always the case. So they're transitioning through to the same response. And if we plot the lateral displacements against the load factor, they just lie on top of each other. And that's a really good test. What I like to do is to try different perturbations. Forces we're going to talk about, displaced shapes we're going to talk about a little bit later on. I like to see if it's insensitive to the initial buckling load and hence imperfection caused by that that kind of cheat load, then that's a pretty good indication that we're not in a particularly difficult type of analysis. Sometimes we will find that it's actually quite sensitive, so we'll actually get a difference in the buckling load based on how we apply that load. That means in real life our structure is going to be horribly sensitive to imperfection levels, the type of imperfection, type of boundary condition, and so on. And that's a big warning to us. So we've got a nice stable condition like this, where we're converging to the same answer wherever we start from. Then again, it's a useful kind of indication. Now, I've gone one stage further. I said instead of applying a push load, let's actually put in kind of imperfection from the word go. So let's put the imperfection in and then apply the load to the structure. So what I've done here is I've taken my linear buckling analysis, taken mode number 1, but it could be anything, as we'll see a little bit later on, and that gives me a particular shape. Now my FEA program here has a little macro in it that says you give me a shape such as this buckling mode in here, I will then update the nodal positions with some scaling factor you give me. Now here we've got the eigenvectors, in other words the mode shape normalized, max normalized to 1, which is very useful. If we don't maximum normalize, it's usually mass normalized, and it comes out as some sort of crazy number up in here. So basically this is a good idea to max normalize. Now my wall thickness here is 0.125 inch. If I get my maximum deflection, or imperfection I should say, about the same order as the wall thickness, that is my rough and ready kind of first stab. Now I might need to go lower than that if it's actually sensitive. I might need to go a little bit higher than that, but that's always a good starting point. So 0.1 times that value of unity gives me 0.1, means the maximum deflection now I've got, sorry, not deflection, the maximum perturbed shape I've got in my model, which is following this mode, is now like that. So the actual model now looks like that. It's kind of stamped onto it. And lo and behold, I run the analysis and I get exactly the same overlay. So again, it's showing that this is really insensitive to whether I put a push load on it, I use some kind of imperfection. So it's all about really the cheating, as we're seeing, is introducing these synthetic kind of imperfections is really the idea. Now I've gone a little bit crazy here and said, well, rather than use mode 1, this is mode shape 6, which is just basically a series of obviously higher modal content. I've scaled that by 0.1 and it transitions to the same buckling shape. So again, another indication that here it's not particularly sensitive to the initial imperfection level to within, say, the wall thickness, or indeed the shape that I get out of it. So again, it's a nicely behaving structure. They're not always going to be like that. Thin wall shells in particular, with very little supporting edge stiffness, like you might get, for example, in a rib, in part of an aircraft skin structure, they can be quite prone to this kind of level of imperfection, which means we've got to do a lot of work to study the sensitivity of that type of structure. So other cheats, we can basically use any deflected shape we like and imprint that on the structure. So linear static is very useful because if I've got some local dimples or ripples, particularly if it's like some sort of local damage, which I think I'm going to be seeing, then what I can do is apply a soft little spot kind of pressure distribution and push my little dimple in there, or ripple, or whatever I want. And if I know this is somewhat similar to that initial imperfection, then that's quite useful. I could look at linear buckling, I could try overall modes, I could try local modes. Again, they may be modeling more like the local kind of effect. I could use a normal modes analysis, which actually gives some very interesting shapes indeed. I've had a great deal of success looking at say struts where the first bending mode, I just use that first bending mode as being the imperfection, or whatever mode really takes my fancy there. Now we can also apply loads, as we've seen, so deflected shapes coming from loads, or linear buckling or normal modes, or directly applying loads such as point loads. So this is the push load rather than the shape coming out of it. And so just to recap, this first paragraph is all about we start with a shape, not a load. And the second paragraph is all about we start with loads. Now point loads are okay, but watch out for singularities. If you've got something which is stiffening and actually resisting that, then you've got yourself a point load. You might well get a singularity causing issues there. We don't really want to be doing that in any kind of analysis. And in nonlinear analysis, the mathematical singularities can start getting mixed up with the actual instabilities that we're looking for. Pressure loads are nice. We can put a soft pressure load on, maybe like a hydrostatic load or something like that. I also like to take pressure loads by mapping displacement fields. So I get a displaced shape from somewhere, such as any of these type of approaches here, and then I produce a field equation from that, or a field data table, and I just convert that to a pressure, and I've got a nice sympathetic soft pressure. I can also be applying inertia loads as well. But again, whatever ones we're going to be using, don't forget, do finesse the cheat in this particular case. And again, we're thinking about our wall thickness just as a first guess in all these cases. So again, the reason for the cheat, James is again saying you pulled that side load from nowhere. Why did you do that? Well, I've got a bunch of soft drink cans in here. And one, no, they're all soft drink. I thought that was a Coors Light for a second. All soft drinks, and basically nice straight walls. No, not in practice. As we know, by the time you pick these things up, handle them and so on, they've got some dents and shapes in them. And that's really what we're trying to get to. The real world is not straight, aligned, concentric, homogeneous material, loaded axially, restrained axially, limited to small deflections as well. These are all the limitations that we've got if we just model this structure just as a cylinder and then try and apply the nonlinear analysis. So that is what was happening in my case. So it's putting in some approximation to the real world eccentricities and so on. Now if you've got great metrology, somebody's gone and actually measured a typical range of deflections you're likely to see on production, then you could use that. But we rarely have that, so we're introducing somewhat, we hope it's somewhat similar to the real case. Here's some cases. This Boeing B-52, it's well known for the ripples occurring in here. The story goes that originally it was just designed for like a 3-man crew, no ejector seats. Then by the time they bumped it up to whatever it is, 5 or 6 men and the ejector seats, you get these semi-diagonal tension fields, actually permanent ripples in the structure. So for buckling, we probably want to model those. And then certainly a lot of work I've done, we get little dints and things happening for either tools, bird strikes, rain, hail, things like that. This is the back end of an aircraft fuselage, and we want to put back these local imperfections and other features. This is where we'll be applying a point load to get maybe a little dimple in there with a particular shape. And again, we've got some measurements in here of the maximum depth, so maybe we can actually put those in there more directly. So sometimes it's overall, sometimes it's more specific kind of values we're putting in. So one question is, how does the linear buckling analysis get away with this? Why don't we need to cheat with linear buckling analysis? Well, it's because of the different nature of linear buckling analysis compared to nonlinear. Linear buckling analysis, we form a normal linear stiffness matrix in the usual way, so that's basically proportional to our geometry and to our material. But then the geometric stiffness matrix is also formed, and that is now a load proportional, sometimes called a stress stiffening matrix. And it's basically a much simpler version than the full-blooded nonlinear stiffness matrix. It is nonlinear, but it's very mildly nonlinear. There's some strict limitations on that. We're assuming small displacement theory. It's linear because it's going to be scaled by a load factor. So whatever value we get here, as we increase the load, it just scales up, which again is not the real true nonlinearity. It's also decoupled from the linear stiffness matrix. So it's a useful little matrix which we can develop in there, and we'll see how we do that in a second, but it's not the full-blooded kind of approach. But what it means is we can do a balance of an equation to say, let's take our stiffness term now, which is our normal elastic stiffness, for whatever type of structure we've got. We've got our geometric, or sometimes called our stress stiffening matrix. The stiffness is a function of the force level that we're applying. So if we apply a lambda, a scaling factor on my applied force, I'm scaling my geometric stiffness as well. So that's the solution that we've got to go through, but I don't have to chase it in a nonlinear way. I can simply say, well, as I'm scaling both the geometric stiffness and the loading together, I can actually do an eigenvalue on that to find when this guy blows up. When these two terms, Ke plus a negative term on here in the stiffness, when these terms take away from each other, I'm going to get terms on my leading diagonal going to 0. Those are the roots I'm looking for. Those are my instabilities. So we can do an eigenvalue analysis to search through those. What values, eigenvalues, are going to cause the instability? What are the mode shapes that come out of that? So the linear term is constant. Geometric term is just scaled by the load factor. In other words, the eigenvalue. Eigenvectors are the mode shapes. So it's a two-step process. We do a static analysis just to find the linear and the nonlinear stiffness. That's all we do. And then basically, and that means doing a static analysis to find the nonlinear stiffness, small scale nonlinear stiffness. And then we do the eigenvalue analysis to find our buckling roots and our mode shapes. So there's no iteration, it's just automatic scaling. So it's guaranteed to work in a kind of in a workflow basis. It's not going to kind of blow up on us. We're not going to have to iterate. But does it give the right answer or not? Again, it is another good question. If our assumptions for this stiffness matrix, which are linear, small displacement, and those approaches, then we're okay. And that's typically true for slender type structures. So here's a very quick run through. Here's a rod element. Here's our axial stiffness, AE over L times the usual matrix. So we're looking at axial deflections. Here's the geometric stiffness matrix, which is all about the lateral response. So this is the axial load, and then the lateral response V1 and V2. Now we do a big cheat, and we assume that geometrically T is actually lined up. So we ignore the little angle which is in here. So again, small deflection theories, lots of assumptions coming in here. So I can actually do a moment balance at both ends there, and I can come up with that little matrix in there. So it's a very simplified nonlinear stiffness matrix, but it's enough to get that stress stiffening term in there. That T is the critical term in my geometric stiffness matrix. So here I've got one rod which is a stiff rod mounted vertically, and then a very flexible rod mounted horizontally. So it's almost like a rod supported by a flexible spring. I'm going to apply a load P up here and then find out what the critical buckling load is. Well, I've obviously applied the load as a positive load, which doesn't make much sense, but the eigenvalue solver can figure that out for us. It's going to find the root, it's going to find what scaling value that should be. If we apply the load in the wrong direction, it'll correct it for us. So we've got the terms in the stiffness matrix here. I won't go through them line by line, but basically this is the combined stiffness matrix, linear plus nonlinear. And now we're going to partition everything out just down to 2 free degrees of freedom. Degrees of freedom which are at V2 and U2, these terms in here. That's my stiffness matrix. So that's the term that comes out of the stiffness matrix. Now I've applied a value of 10,000 pounds in the vertical direction, which is a bit boring. It just shows me that I get no lateral deflection at U2. V2 is 0.09 inches. That's a static solution. Now we're not really interested in that. We turn it on its head and say do a buckling analysis. Well, what I've done is to pull out the terms in the stiffness matrix and actually have a deeper look at them. So we've got the linear terms, AE over L, and then we've got T over L, which is the nonlinear terms. And if we make T negative, which is what the solution will be, then one or other of these terms is going to knock out. Got a term on the leading diagonal. What level of T will that occur at is basically my linear buckling analysis. If I write these equations out, so basically that's the stiffness. So this is the stiffness times lambda, so I'm multiplying that by lambda, that's my deflection, there's lambda times my load. And I can do a simple back calculation and say when does the term go to 0? So that term plus that term goes to 0 at that particular load level, and it's an eigenvalue of minus 107, and multiplied by my load, then that's the value. And if I run a linear buckling analysis, lo and behold, I get exactly the same number coming out, which is no surprise. So that's what the linear buckling analysis was doing for us. That's why it's different from nonlinear buckling analysis. Lots of assumptions in there, no iterations, no chasing nonlinearity, not even chasing geometric nonlinearity. So let's see how we get on if we shorten this beam now to 90 inches. So I'm going to do a linear buckling analysis on that. I get the same mode shape. Eigenvalue is this, multiplied by my arbitrary applied load, I get 34,000 just over. Now the classic Euler solution gives an eigenvalue just a little bit different and actually gives a slightly higher value. Now that's getting a bit irritating. Why is the classical solution different from my FEA solution? It's the same problem I'm setting up. Well, it turns out that the eigenvalue solution, the Euler solution, doesn't include stiffness, shear stiffness of the beam. An FEA element will include the shear stiffness, but if you ever want to check something which is no shear stiffness terms, just set it to 0, set the shear area to 0, and then you get back to the classical result. So that's an easy check. If I do that, then I'm spot on with my answer here. So it's okay. FEA is matching the limited application of a flexural bending only beam response in there. So let's look to see where we are in this curve we looked at before. Remember, we're typically talking about a length to radius of gyration ratio, because we've got a known radius of gyration. This little app just very conveniently doesn't normalize it, just gives me a length to look at directly. We're down to, I think it was 90 inches here, so basically at that point we're actually off into the danger area. This is the transition, so the Euler curve is going up in here, that's our linear solution. Now we are deep into the nonlinear solution, so this is actually an intermediate rod or beam, and it should not be done using linear analysis. The implication of the linear solution is way up here somewhere, and the trouble with a linear buckling solution is if we get it wrong, then it's highly non-conservative. So the Johnson formula is a formula which is an interaction formula here, basically between the Euler at that transition point and our yield point here, and here we've converted it to an equivalent force. Again, the Johnson formula isn't universal for a large class of well-known struts, beam shapes and so on. It's well proven from theory and lots of test evidence. civil engineering in particular, it's a well established. If we got a general shape solution, we don't have a Johnson formula for that. We've got to go in and explore that. So if you're not sure, you think you might be here, then you should be really running a comparative nonlinear analysis just to show what's going on. So why bother with nonlinear buckling? Well, because here we've exposed limitations of linear buckling in that particular case. So we're going to now do a nonlinear buckling analysis on this same problem, and we now see again the transition occurring. The nonlinear buckling using an elastic material, so no material nonlinearity. I've increased my unit load up to 45,000, so about load factor about 7.75. I get 33,750, which is very high. Yield is only 16,000. That gives me an axial load maximum 22,000. So again, I got a silly result. I can't get all the way up here because in that particular case, plasticity is going to play a role. Now the Johnson equation will look at form factors and will bring in plasticity in that particular case. So again, I kind of stumbled across another limitation. This particular case, I should be bringing plasticity into my buckling calculation, my nonlinear buckling calculation. Sometimes you do, sometimes you don't. Sometimes it's going to be starting off as a linear buckling, elastic response, and then transition very rapidly to a plastic response. Sometimes it will actually buckle after it reaches the plastic state, and that seems to be the case here. So I'm going to rerun this in this particular case with now elastic perfectly plastic material. Now I don't particularly like the elastic perfectly plastic. It means there's no work hardening, but these particular beam elements in this solver only handle elastic perfectly plastic. They basically form plastic hinges. So in that particular case, I reach a much lower load level and I get a load of 21,000. So it's getting closer to the Johnson equation of 18,500. So the beam material model, it basically is forming a plastic hinge at that point. Notice the deflections are very tiny. So the push load came off, I took it off. It still keeps that eccentricity building, and then the buckles at that point. So these are tiny little deflections now, not the bigger deflections we saw previously. So in fact, I actually dropped that side load down to make sure that I wasn't interfering with the end result in here. So still not quite there, but that's about as far as I can go with the beam elements. So what I've done now is I've transitioned to shell elements and said, well, let's try shell elements. And I've set up exactly the same problem, same geometry, but now with thin shell elements. So I run first off a check linear buckling analysis. I know this is going to be wrong, but I just want to check to see if I get similar answers to my linear buckling analysis with beams, and I actually get a pretty good answer coming out. Critical load is 34,000. We know that we're going to have shear stiffness in here by its very factor, but it's pretty good, pretty close. Now let's do the nonlinear buckling analysis, and I'm going to have elastic plastic material. I've actually put about 10% of Young's modulus in as my plastic modulus. It's a very rough and ready way to do it. Get some work hardening in. Now it's force controlled, which means once it reaches its plasticity, it's going to develop plasticity across here very rapidly. It's going to form a plastic hinge. It is still going to collapse, but it's not an elastic perfectly plastic hinge. It's still able to develop some sort of plastic field in there. If I look at that, I get very close indeed to the Johnson equation. So the Johnson equation is obviously looking at form factors in a real rectangular beam, and we're doing something very analogous to that when we see the growth of plasticity here in our nonlinear model. So again, very small deflections, and we're getting that buckling occurring. Now I was curious to see if it's really a runaway collapse. Once that beam starts to go, there's not much to hold it back. What I did was to still keep a force controlled method, but used an arc length method. Arc length method is a bit more sophisticated because instead of ever increasing that force, you can never backtrack. It actually searches backwards, if you like. So it actually reaches the critical buckling node there, and then says, well, if I soften the load, what happens next? So it's rather like, it's similar to a displacement controlled time solution. In other words, hey, let's back off that load rather quickly so we don't collapse and just crush our structure. Let's see what it can actually handle now. So we're taking the load off. It's softening very, very clearly, and it does actually allow us to see more of the kind of shape that it would develop as that plastic hinge is developing further, but again it's just softening it off. So it's okay, it's running away, let's take the load off quick to see if we can explore a little bit more what's going on. We would do this more probably if we're going to get the next configuration was a stable configuration. So we buckle, it then transitions to another stable configuration. We really want to understand how it does that, so we can chase post-buckling a little more carefully, rather than something like our beam is just going to fail catastrophically. So in summary, the push loads, they're really and force shapes that we used in nonlinear buckling. Honest Jim, this Jim Garner again, we weren't cheating, we're just really simulating real world imperfections in the best way we possibly can. Now linear buckling, we don't need to cheat. It has the advantage of simplicity, but has limitations we've seen in many areas. It is small displacement, there's no stress stiffening, there's no geometric nonlinearity in it, so it has limitations, and the biggest limitation is if we've got something which is not a slender structure, it's over predicting the load level which is going to buckle. Nonlinear buckling is more difficult to set up, but we know if we cheat a little bit, we can model post-buckling. All forms of nonlinearity can be in there. Soft stiffening, softening, plasticity, geometric nonlinearity, they're all in there. And if there are any doubts about whether we use non-conservative linear buckling or not, then we would go to nonlinear buckling. So that's just a quick summary. Buckling is actually, and associated instability is a huge subject area. This is just the tip of the iceberg. I've just covered it in a few minutes. I've gone a little bit past my timing. I apologize for that. It's a very, very big topic. So thanks very much for watching. This video is going to be posted on YouTube and our websites, so watch out for the link. Next week we're going to be talking about high cycle fatigue or low cycle fatigue. What's the real difference between them? Is it just a number like 100,000, 50,000, or is there something else going on there? And the answer, of course, there is something else going on there. So at that point, normally we would then transition to Q&A. Because I've had to redo this video because of issues with the internet, I'll stop at this point and then I'll restart and we'll move into a kind of a more curated Q&A there. So thanks very much for watching, and if you're going to watch the Q&A, I'll pick up shortly with you there. Thanks very much.